need to, may not have to, go to the at the very next instant, at the boundaries, because pressure is U or equal to Q on the same boundary and is equal to atmosphere of 0 on the outside boundary, pressure will be anticipated because 0 here, and which means that pressure is as we have seen. Is 0 here, 0 here, and some pressure is again participated in second, so the very little bit from the initial value, however, it will still be maximum physical. So, we can from here, wait, concentrate the organization of this. If Z is the coordinate, which is like the
ma'am, no issues, ma'am. I can wait, ma'am. Not even 11 o'clock, ma'am.
You must be zero. And not only at the initial instant, but once you and person is evaluated. And this is how the values will be. Suppose I suppose we get that and some values of the one to one. Here we have 1 to be 0.0.
Hello? Hello?
Yes, ma'am. Mr.
Yeah, yes, Varsha, no issues. You can take your time. Hello, Varsha.
Kritika, it is visible, ma'am.
Yes,
Yes, ma'am. Now it's visible, ma'am.
Yes,
Visible, ma'am.
So now, ma'am, I have taken it to the full screen mode, ma'am. Is it visible, ma'am?
Yes, ma'am. It is visible, ma'am.
And before I start off with the presentation, I would like to thank the management of Hindustan College of Science and Technology, the head of the department, Dr. Uma ma'am, and the coordinators of the department for giving me this opportunity to share my experiences on Boolean algebra with you. Now, I'm Yamuna. Ma'am gave me a very nice introduction. Thank you, ma'am, for that. I'm an associated professor in the Department of Mathematics, VIT, and I belong to the Vellore campus. My email ID is available here. At the end of the session, for any queries, you can always write to me, please. Now, the topic that I have taken for the day is biological applications of Boolean algebra. Now, this is my actual experience of reading an article on Boolean algebra. Few days back, I happened to read a paper on Boolean algebra. Now, this paper was quite interesting for me for one reason that the normal Boolean algebra properties that we teach inside the classroom. I had been teaching discrete maths for years together. Then I suddenly understood from this paper that this can be applied somewhere relating biological properties also. So I thought, let me present it here in today's presentation so that it might be interesting and later it could be applied in some research domains also. So the presentation, I want to split up into different parts. Maybe in the first part of the presentation, I want to introduce the basics of algebra, which I might be using later. Then we are going to biological applications of Boolean algebra. So I want to bring in a bit of amino acid properties and other stuffs which may be a necessity. And then I want to go for the Haze diagram representation of the original amino acids which the author has done. Finally, the author concludes with the note that whatever we have been doing now may be used for predicting what we call in medical terms as mutation. So this is what I have planned for the day, and let me go into the Boolean algebra part of the presentation. Now, Boolean algebra. In my perspective, I would always like to one second, go with the presentation in this fashion. History, according to me, is slightly important. So I would like to recollect a few things here. Let us look at the photo of some great person here. This is the photo of a person, and one more combo I have here. Now, this person is actually George Boole. He was born on 2nd November in 1815 at Ballintemple, County Cork, Ireland. Now, I want to tell a few words about this person before we actually go into the details of algebra. Let us look into the details. In the year 1834, he opened his school in Lincoln at an age of 19 itself. And he started publishing regularly in Cambridge Mathematical Journal. Now, why all this becomes important, I shall let you know later. And one more. In the year 1842, he published an article on a general method of analysis. For this article, he received the Royal Society Medal in the year 1844. And I have a small note about it. He was appointed as the chair of mathematics at Queen's College in the year 1849, and he became the first professor of mathematics in the same college. Now, these are all very common things in a professor's life. Let us see why this becomes very important. Now, let us see what he wrote in a letter. This letter is dated 2nd January 1851, and he had written a letter to a person called Thomas. Let us have a gist of this letter. He is writing, I am now about to set seriously to work upon preparing for the press an account of my theory of logic and probabilities, which in its present state I look upon as the most valuable one, if not the only valuable contribution that I have made or am likely to make to science, and the thing by which I would desire, if at all, to be remembered hereafter. So this is what he wrote in the year 1851, and in the year 1854, he published this article, an investigation into the law of thoughts, on which are founded the mathematical theories of logics and probabilities. And his dream did come true. This began a new era of logic, what we call today as Boolean algebra, which now finds applications in computer construction, switching circuits, etc. I get back to his letter. He wrote in his letter that I would desire, if at all, to be remembered hereafter. Boole's dream did come true. Today, what we call Boolean algebra is because of this great person. I have one more small slide about this person. We should be reading this. One day in the year 1864, he walked from his residence to the college at a distance of 2 miles in the drenching rain and lectured in wet clothes. The result was a feverish cold which soon fell upon his lungs and terminated his career. So he expired in the year 1864. The reason is something which we are reading here. He was going for lecturing in a heavy rain, and this was the note of McFarlane. the final conclusion I would like to give here about Boole. Boole system of logic is but one of the many proofs of genius and patience combined together. And I think you can read this part. I want to read the last part alone, where in this, when Hobbes published his computation on logic, he had a remote glimpse of some of the points which are placed in the light of the day by Mr. Boole. So this is an appreciation of De Morgan, whom we have heard many times. Now, why all this becomes very important? We are looking into Boolean algebra for the day. I was looking for his bibliography. Surprisingly, I found that Boole did not go for any academic degree at all. He started his own school for one reason, that he had a poor background or not much to do background, and he had to go for a job. For that reason, he started his school on his own along with his maybe brothers and sisters. That is what I had read. And it is astonishing that what we learn today as Boolean algebra is done by this great person, and he wants him to be remembered for this. And he never did go for any academic degree. He just went for schooling only. So this was surprising for me, and I wanted to share my experience with you. A person with no academic degree has gone for a revolution in mathematics. That is what I should tell. And he was a dedicated teacher. He had no academic degree, and he became the first professor in one reputed institute, a university also. So with these few words about Boole, I want to go back to the Boolean algebra part. Now, whatever I'm recollecting back is what we have already learned in schools and what we teach in colleges. Any professor who is listening to me, kindly excuse me for the 10 minutes, because you might have been teaching this, and this is a faculty development program and students might be listening. So I just wanted to recollect a bit of what we are teaching inside the classes. Now, relations. We know that a binary relation defined on a set is a reflexive relation if x is related to x for all x in x. And we know that it is symmetric if x related to y implies y related to x. And antisymmetric if x related to y and y related to x implies x is equal to y for all x comma y belonging to the set x under consideration. And finally, transitive property, if x is related to y and y is related to z, then we know that x is related to z for all x, y, z belonging to x. So these are certain things we learn right from school, and we are very comfortable. We remember if it is reflexive, symmetric and transitive, we call the relation to be as an equivalence relation. And if it is reflexive, antisymmetric and transitive, we call the relation to be as a partially ordered relation. And this is notational convenience. Less than or equal to denotes a partially ordered relation. And if less than or equal to is defined on a set P under consideration, we generally denote it by P comma less than or equal to. This is what we normally denote things by. So today we are going to stick on to a partially ordered relation with the notation P comma less than or equal to. Now, let me take an example. This is a very common example which is given, or the very first example we give inside the classroom. I take x to be any set, and rho of x is the power set of x. It's a set of all subsets. Now, the partially ordered relation that we are defining here is a subset of. We need to verify if this is going to be a poset for us. It's very obvious thing. A set is contained in itself, so it will be a reflexive relation. And we know that if A is contained in B and B is contained in A, then A is supposed to be equal to B. So the relation will be definitely an antisymmetric relation. And if A is contained in B and B is contained in C, then A of course will be a subset of C. That means that the relation is a transitive relation. And with all these put together, it becomes a partially ordered relation. A very obvious common example given inside the classroom. With this note, I want to go for constructing a Haze diagram. A Haze diagram is a diagrammatic representation of a partially ordered relation or a partially ordered diagram. We know and we how to do things. These are few points for you. Vertices are represented by a small dot, and we have the number of vertices will be equal to the number of elements in the set. And x is slightly below and y will be slightly above if x is less than y. And we draw a line between x and y. if X covers Y for us. So this is how a Haze diagram is basically constructed. But instead of reading it, let us go for an example. I take the same set. Just now we have shown that the set of all subsets with respect to the partially ordered relation less than or equal to is going to be a co-set for us. I'm taking the set of all subsets. We totally have 2 power n, that is 2 power 4 equal to 16 elements. That means that in my Haze diagram, basically I'm going to have 16 vertices. Now, let me choose the least element here. I'm choosing the least element to be as an empty set for one reason that phi is contained in all the sets. Phi is contained in 1, 2, etc. It is contained in 1, 2, 3, 4 also. And next level elements, you have to slightly draw it above. And I take this as 1, 2, 3 and 4 here. Now, we also know that between elements in the same level, we cannot have a partially ordered relation. Now, the relation that we have taken here is contained in or is a subset of. So, definitely none of these 4 elements are subsets of each other. So, we can draw edges. Phi is a subset of 1, phi is contained in 2, phi is contained in 3 and phi is contained in 4 also. Now, let me take the next level elements. This has to be slightly above whatever you have already. Now let me draw the edges. 1 is contained in 1, 2, 1, 3, 1, 4. 2 would be contained in 1, 2, 2, 3 and 2, 4. Similarly, 3 and 4. So this will be the diagram for us. Now if at all Haze diagram is new for anyone, the stuff over here is phi is contained in all the elements. So technically speaking, I am supposed to draw a line from phi to 1, 2, 1, 3, etc. Say for example, I include one edge here. I have drawn a line from phi to 1, 2. 2 reasons here. One reason is if you keep on drawing lines, the diagram becomes more clumsy for us and difficult to understand. Second, we know that transitive property is satisfied. That is, I have phi to be contained in 1 and 1 is contained in 1, 2, which means that phi automatically will be contained in 1, 2. So by transitive property, it is understood. That's what we mean by the third point. We draw a line only if X covers Y. So in here, phi covers 1, 2, 3, 4, but phi does not cover any of these sets here. So this line may not be an 8. It is understood obviously by transitive property. So I am removing this edge from here. That's what we are trying to do. Remove this edge from here. Then go for the next level elements. So now next level elements, I go for doing this. Now it is easy for us. We just need to draw the edges. 1, 2 is contained in 1, 2, 1, 3 and similarly the other edges. I am using set property here. One by one we try to draw the edges and finally 3, 4 is contained in 1, 3, 4 and 2, 3, 4. So the highest element we know that it's 1, 2, 3, 4. Every element will be contained in 1, 2, 3, 4. So this diagram we call it to be as the Haze diagram. And only one more part of algebra, Hamming distance. Hamming distance, we know that it is defined on binary numbers. And speaking a very blunt definition would be like you look for the number of questions in which they do not match with each other. That is what we define it to be as a Hamming distance. Let me take an example. I have taken this and in the first position, it is 1 and 1 for us, so they match with each other. When we look at position 2, it is 1 here, whereas it is 0 here. And in the third position, it is 0 and in the second string, it is 1. And then it is 0, 1 and 0, 1 here, they match with each other. And finally, it's 1 here and 0 here, they mismatch with each other. So the number of mismatching is 3. That means that Hamming distance is going to be 3 for me. Now let me go here. I have taken 2 strings. First position, it's 1 and 1, they match. Second, it's 0 and 1 mismatching. Third position, 1 and 0 mismatching. That means that Hamming distance is equal to 2 for us. So with this, we are done with the algebra part of the presentation. This much only for the day. So all we need to know is a partially ordered relation, a Haze diagram, and maybe a Hamming distance also. Only 3 properties from maths for us. with this small note, let us go to amino acids. Now, when we speak of amino acids, we cannot skip a DNA. So let us go to the biology part. DNA, we know that it's a hereditary material available in almost all the organisms. And we know that every cell in our body has the same DNA. And it is made up of 4 chemical bases. I have listed out here adenine, guanine, cytosine, and thymine for us. And this is a double helical structure of the DNA, which we are very much familiar. And when I say a DNA sequence, I mean a sequence of this category. Now, we are with amino acids, so we need to compare a DNA with an RNA. Now, we understand here that it is a double helical structure and it's a single helical structure here. The only difference is I have thymine over here. The hydrogen carbon bond which is available here is not available in uracil. That's the difference between a DNA and an RNA. Let me go for slightly comparing the properties. A DNA is used in long-term storage of genetic information, whereas the role of an RNA is to transfer the genetic code from the nucleus to the ribosomes to make proteins. That's what they tell here. And maybe this information may be useful. This molecule, it is used to store genetic blueprints in primitive organisms. And the second point, we have already seen, it's a double helical and single helical structure. And it varies in the uracil thymine basis. Now, DNA is self-replicating, whereas RNA is synthesized from a DNA. Like what happens here is, you have the double stranded structure, and it gets unveiled or it gets removed. And then the hydrogen bonds are removed from there, and one part is synthesized, which we call it to be as the RNA. And the base pairing is ATGC here, whereas it becomes uracil over here. It is AUGC for us. Now, DNA to RNA to protein for us. We know that DNA is double stranded for us, as you see here. And as I told you, the double helical structure, it gets removed and it becomes a structure like this, and one part of it is extracted as an RNA. So what you had as thymine now becomes uracil. You can see it here. The T has become U. The hydrogen carbon bond is no more existing. It becomes an RNA. Now every bit over here you are going to call it to be as a nucleotide, and 3 nucleotides combined together you call it to be as a codon, and each codon is representing a protein. So the last row over here actually represents proteins for you. This is what happens in our body maybe on a daily basis also, the DNA to RNA to protein. Now let us look at this table. This is the table that we are going to stick on to throughout the presentation. And this is an amino acid codon table. I have taken an RNA table. As I told you, these alphabets are representing amino acids. P represents proline, and S represents serine, L represents leucine, and so on. And most of the amino acids have more than one codon here. Like if you see glutamine, it is made up of CAA, CAG. Cysteine is made up of UGC and UGU and UGC. So this is the codon structure, and basically there are 64 codons for us. Now, there are many properties which are satisfied by amino acids. I have listed out only a few over here because we cannot go for listing out all the amino acid properties because that is not the target of the day. Now, here we have acidic property, acyclic property, aliphatic, aromatic. It is basic, charged, uncharged, hydrophobic, hydrophilic. And whatever doubts you have over here in the table are representing the properties satisfied by the particular amino acids. Now what we are going to concentrate here is the hydrophobic property. So I have a small video for you. It's just a 1-minute video because we need this. Ma'am, is the video visible, ma'am?
No, ma'am.
Ma'am, is it visible or not visible, ma'am? Ma'am, it's a black. You are seeing an empty screen, ma'am. Black
Yes,
screen.
ma'am.
Yeah, yes. Yes. I'm playing the video now.
Okay, ma'am.
think the visual representation was much better for understanding. Like now we understand what is hydrophobic and hydrophilic. Hydrophobic means it does not mix with water, and hydrophilic means it mixes with water. That's what we understand. Now I have a small slide here for you. Here yellow represents hydrophobic. That's what we are trying to look at now. And white represents hydrophilic. And we have a strange cysteine one, which is neither hydrophobic nor hydrophilic nor negatively charged nor positively charged. So you look at the screen here, some of the amino acids are hydrophobic, that is they will not mix with water. That's what we understand. Hydrophilic means they get dissolved in water easily. Like valine is hydrophobic, whereas if you see here, serine is going to be hydrophilic for us. So this is the major property that we try to concentrate on, and this is important for us. If you have U in the second position of the codon, then it represents a hydrophobic amino acid, and having U in the second position, A in the second position will represent a hydrophilic amino acid for us. That's what the authors also claim here with this. I have a few pictures here. Actually, I wanted to show all the pictures of the personalities who had discovered amino acids, but unfortunately, I could not collect all that from online. I just want to write one line over here, like the study of or the history of amino acid dates back to the year 1789, where several types of proteins were actually distinguished. Initially, they were called as albumin, and leucine is understood to be the first amino acid to be isolated in the year 1819. Later, Mudler determined the elemental composition of several proteins, and in the year 1838, this name protein was given from the Greek name, which means that standing in front. And these two persons are actually known to have discovered amino acids, and maybe this person, Ernest, he had discovered phenylalanine. So with these few words, I would like to go to the original part of doing Haze diagram for amino acids. See, when we are trying to do a Haze diagram, we require various things, like first thing is I need to define a partially ordered relation, a suitable partially ordered relation. That's what we mean here. And second thing is we need to draw the Haze diagram. Haze diagram, we are trying to do it for amino acids. Randomly, this cannot be done. This needs to be done with some biological properties. Let us look into the details now. Now, what they initially have done is they have gone for binary conversion. Like the AUGC as converted as 00, 01, 10 and 11. This is the initial stage of doing things. Now whenever we construct a lattice, we know that we also can construct a dual of the lattice. Less than or equal to is a property, means greater than or equal to will also be a property. So for the binary conversion, for the dual, it will be 00 becomes 11 for us, and for A 01 would become 10, for U 10 would become 01, for C 11 would become 00. So this is for the prime lattice and this is for the dual lattice. This is the binary conversion. So the first thing that is done is going for a binary conversion. Second, a partially ordered relation need to be defined. This is how the partially ordered relation is defined. Here B of x is going to represent a string of binary numbers. Or and represents the usual or operation and the and operation here. And the definition is alpha is comparable with beta for any two amino acids alpha and beta. If at all negation alpha or beta value is going to be equal to 1 for us. This is how it is defined. Now let us verify if this actually is a partially ordered relation. So first property, reflexive property. Let me take the table here. When alpha takes the value 1, negation alpha is 0 and it's 0 and 1 here. Now we know that when we go for the OR operation here, anyways this value is going to be equal to 1 only for us. That means that negation alpha or alpha equal to 1 for you, which means that this relation is a reflexive relation for us. Next, antisymmetric property. If I go for antisymmetric property, I need to assume alpha is related to beta and beta is related to alpha. That means that negation alpha or beta equal to 1 and negation beta or alpha would be equal to 1 for us. Now let me take the truth table here. When negation alpha is 0 and my value beta can be equal to 0, or when this is 0, beta value could be 1. Similarly, when negation alpha is 1, beta could be 1 or 0. But now the property that need to be satisfied is negation alpha or beta equal to 1. So if I have a 0-0 combo over here, the property will be violated. That means that this combination is not going to be possible for me. Let us look at the rest of the combinations. When beta is 1, negation beta will be 0. When it is 0, it is 1. And when it is 1, it is 0. So now the alpha values will be 1, 0, 1 respectively. Now once again, antisymmetric property we are trying to verify. So we know that negation beta or alpha also should be equal to 1. That means that we cannot have a 0-0 combo over here because our operation here will give us a 0. That means that last row is also not possible for us. Now compare alpha and beta. It is 1-0 for beta and it is 1-0 for alpha also. That means that alpha equal to beta for us, which means that antisymmetric property is satisfied. So whenever alpha less than or equal to beta and beta less than or equal to alpha, we get alpha to be equal to beta. This has been carefully defined so that all the properties are satisfied. The last property, transitive property. So here, let us take 3 amino acids, alpha, beta and gamma for us. Alpha will be related to beta, beta will be related to gamma. Now, the property that should be satisfied as per the definition is negation alpha or beta is 1 and negation beta or gamma equal to 1. So let us once again get back to the truth table. As we had already checked, negation alpha and beta. When negation alpha is 0, beta could be 0. When negation alpha is 0 here, beta could be 1. And again, it could be 1, 0 and 1, 1 respectively. As we had already checked, negation alpha or beta, it has to be equal to 1. That means that this 0-0 combo is not going to be possible for us. So I cancel this for me. Once again, the same story. I need negation beta or gamma value to be equal to 1. The same is going to happen here. So the rest of the rows alone we shall consider. It is 0, 1, 1, 0 and 1, 1 respectively. Now, let us check with the data values here. Negation alpha, it is 0, 1, 1 and gamma is 1, 0, 1. So if it is 0 here, it is 1 here. When it is 0 here, it's 1 here. That means that in the product, the value will be equal to 1 altogether. When I take negation alpha or beta, the value would be equal to 1, 1, 1 respectively, which means that negation alpha or gamma equal to 1. That means that transitive property is satisfied. So it's reflexive, antisymmetric and transitive, which means that the relation is a partially ordered relation. So the first thing is, all the amino acids, they are made as binary strings and a partially ordered relation is being defined here. Next, we need to go for constructing the Haze diagram. See, as we have already checked, this is not a regular Haze diagram. We are going to do it for amino acids. So we need to verify with the biological properties also. The author defines 2 properties here. Both the codons G, G and G and C, C and C have the same minimum hydrogen bond numbers and they code for amino acid side chains with small polarity difference. This is the first note and they have another note. Although the codons U, U, U and A, A, A have the same minimum hydrogen bond numbers, they code for amino acid side chains with extreme opposite polarities. Now the point over here is, they have the same minimum hydrogen bond numbers in both the cases. But here, polarity difference is small and here they are extreme opposite polarities. With this, the author concludes this. Maximum element in the prime lattice is C and the minimum element is G here. And from the second note, the authors conclude U and A are not comparable and hence they should not be the maximum and minimum element in a lattice with biological meaning. See, we are trying to fix the least element and the greatest element of the lattice, but care has been taken on how this is being done. So U and A are uncomparable, not comparable, because U in the second question means hydrophobic and A in the second question means hydrophilic, and they cannot be the maximum and minimum element. With this note, now we know that the minimum element in the prime lattice is C, C and C. So let us go for constructing the Haze diagram. Least element is C, C and C. That's what we have checked. Now let me show the vertices first. I get back here. These are the vertices. Now let us look at a bit carefully here. I have C, C and C. Now what they try to do here is, U could be in the first position. G and G is fixed as a maximum element. So they don't take G under consideration. C is U and A are taken. U could be in the first position, second position or third position. So these three vertices are taken here. Similarly, A could be in the first position, second position or third position. That is how the first level elements are constructed here. Now we can go for drawing the edges. One edge, second edge, 3, 4, 5 and 6. So this is how they start initially with. Now let us go for the remaining vertices. I shall first fix the vertices. I think I have done. Now let me draw few edges first. Lines 1, 2, 3, 4 and 5. Now let us look at how this is being done. See, the thing is, I have C, U, C here. Now U in the second position is going to represent hydrophobic property. So this U will not be disturbed over here. It remains back undisturbed. What happens is the other two are U and A. So I can have C is replaced by U here, or C can be replaced by U here. That means it becomes UUC and CUU for us here. Otherwise it could be replaced by A, which means that it becomes AUC and CUA respectively. And finally, this U will be replaced by G for us. That is how this is being done. So I have UUC in the third position, first position here, and in the third position here, A in the third position here, A in the first position here, and U is replaced by G. Now the same thing happens with UCC. This U will not be disturbed and the C will be replaced by U first, UUC, then UCU, then replaced by A. It becomes UAC, UCA, and finally this U will be replaced by G, which is GC and C. Let me draw the edges here. Yellow color edges, 1, 2, 3, 4 and 5 for us. Similarly with the next codon, U will not be disturbed, 1 edge, 2 edge, 3 edge, 4th one and 5th one. Now the same stuff will be done with this combo CCA. A will not be disturbed because it's going to represent hydrophilic property. So it becomes UCA, then CUA, then ACA, CAA and finally CCU for U. So let me draw the edges. First edge, 3, 4 and 5 for us here. The same stuff will be repeated. Pink color edges. And finally for the last codon, turquoise color I have used. So we have done with the understanding part of the Haze diagram. Now we know, or we had already checked, between elements in the same level we cannot have a partially ordered relation. And between elements in different levels we will have a partially ordered relation. Let us check if this is happening. I have taken two elements in two different levels. I need to verify if the partially ordered relation is happening. That I need to verify whether negation alpha or beta equal to 1. So I go for the binary conversion. CUC and CGC is taken as the binary string. Let's go for verifying this property. This is equal to 1 here. That means that between elements in different levels, the partially ordered relation is satisfied. Now let me pick two elements here. I'm picking elements in the same level. there should be no partially ordered relation between them. Let us check if this is happening here. Go for the binary conversion, then negation alpha or beta. We have a 0 term here. It is not equal to 1, 1, 1. That means that between elements in the same level, there is no partially ordered relation. So this is a perfect Haze diagram for us. Now it looks very beautiful and it is constructed with biological meanings also. I want to show a small picture here. This person, he is Helmut Haze, and he was born on 25th August 1898 at Prussia. See, though Boolean algebra was discovered by Boole, this beautiful representation of drawing or representing a partially ordered relation as a Haze diagram was actually discovered by Helmut Haze, and we call it as a Haze diagram after this person. I wonder whether he would have imagined that this would be taking this much turn in future, and I just wanted to show his face because we often learn Haze diagram. Let me not go into the history part because otherwise it would become a history class for us. Now, this is the entire, just hold on. I'm sorry about this. This is the original Haze diagram that the author had constructed. Now we see some colors here. Black color, then gray color here, and very light gray color here. So black color is the second base is U for us, and maybe light gray is A for us. We know this is hydrophobic and this is hydrophilic for us. That is a transversion from hydrophobic to hydrophilic over here is taken into consideration. See, care is taken about how the vertices are labeled, how it is constructed, and the other stuffs are taken care. Let us see few properties here. Codons will be in the chain with maximum length only if they are comparable. Comparable means they have to be in the next level. Like we have 7 levels here, starting from CCG to GGG. That means that 6 edges could be there. Let us check with the edges. GGG to GAG, then to AGG, AAG, then to AAA, then to AAC, CAC, and CC and C for us. So this is one maximum possible string, and the author tells that there are 720 such chains. One more note from the author. Codons that code to amino acids with extreme hydrophobic differences appear in different chains with maximum length. See, what they try to convey here is very simple. Suppose I take a property here. I take GGG to GAG, it's highlighted. I'm not this is hydrophilic. I'm suddenly not going to jump to a hydrophobic property. So hydrophilic will be in a separate chain and hydrophobic is going to be in separate chain. Extreme properties will not be in the same chain. That's what they tell here. Next case for us here. Algebraic properties of codons in the Boolean lattices are associated with the hydrophobic properties of the amino acid. So this represents hydrophobic for us, and here it is hydrophilic with 720 such chains. Now we understand why we are trying not to draw too many edges. Already there are too many lines here. If we try to represent transitive property also, it becomes too clumsy for us to understand the diagram. So larger the Haze diagram, for ease of representation, we are avoiding certain edges, and that's why things are this way here. Now let us check out this property. The algebraic property of the genetic code Boolean lattice will help us to understand the hydrophobic changes in the gene mutation. Now we concentrate on the word gene mutation here. That is going to be the last bit of the presentation, mutations for us. It's 11:45. I think I have another 15 minutes. It should be all right. Mutation. Now let us get back to what is mutation. See, mutation occurs in our body. Like now I am presenting, or I told you now the time is 11:45. That means that I'm able to understand it's 11:45. I am speaking to you. You are listening to me and you are understanding what I'm speaking. Now, all this is happening in our metabolism or in our body due to one reason. Proteins are doing their job at the right place and at the right time. See, when I tell at the right place and right time, it really matters. Suppose I have taken breakfast in the morning And after taking breakfast, the protein sent a signal to my brain that I'm hungry now. I feel hungry. That means that the job is not done at the right time. So if something fails over here, either it is not done at the right place or it is not done at the right time, then changes occur in our body. That is what happens is mutation occurs in our body. And in medical terms, this changeover in the protein, they call it to be as a genetic disorder. I have an important note for you. Like what we call as genetic disorders are not actually caused by the genes themselves. It is actually caused by the mutations that make a gene function improperly. This is an important note for us. So genetic disorder means a mutation occurs in the gene. Now let us see what is a mutation in a better sense. There are different types of mutation, and what we saw in the Haze diagram is gene mutation. There are different kinds of gene mutation. We are not concentrating on chromosome mutation, and this table lists the possible mutations for us. Maybe we are not going to concentrate on every possible mutation. Let me explain what happens actually in the DNA by one type of mutation. Like you have a sequence of histone over here. That means that the combo is CAT, CAT, CAT over here. Suddenly one change occurs in a nucleotide. A is replaced by C here. When A is replaced by C, what happens? Instead of CAT, we are having it as C, C and T. That means that histone is replaced by a proline here. So the entire sequence is disturbed. That means message is not transmitted properly. That's what I should tell you. It was transmitted through a sequence of histones. Now suddenly proline has come into picture here, which means that the entire metabolism changes for us. A malfunctioning of the protein occurs, which we call it to be as a gene mutation or amino acid mutation. One amino acid is changed into another. Histone has become proline. Now there are different types of mutation depending on how and where they are occurring. Nonsense mutation, insertion mutation, deletion, frame shift and repeated expansions. Now what happens actually when all this happens? Technically speaking, when all this happens, message is not transmitted, proteins are not functioning proper, they don't do their right job at the right position at the right place. So what happens is genetic disorders. Now I often use the word color blindness because that I understand in a better sense. Some of us cannot see certain colors or we cannot see colors at all. This is caused by genetic disorder only. And somewhere learning in school, we recollect something as Down syndrome, Turner syndrome. Our teachers have been teaching this as Kahneman disease. All these we understand today as it is caused because of different kind of mutation which occurs in our body. Now, before we go to actually identifying mutation, I want 2 minutes for telling something, getting back to history once again. See, so many things we have checked from morning. We started off with Boole, then we went to Boolean algebra, then we shifted over to amino acids. When we went to amino acids, we know that DNA forms a big story over here. Let us see one important person now. I would like to show the personality to you. These are images of the person. This person actually is Friedrich Mischer. He was born at Basel, Switzerland on August 13, 1844, and he graduated from Basel's University Medical School. And let us see what this person has done. He actually discovered DNA in the year 1869. And how he discovered DNA is very interesting. See, he had discovered it from pus cells from bandages of war soldiers. See, this is a very big thing what the personality has done. He had collected the bandages and he went for picking the pus cells from there and he had extracted things from there and he had discovered DNA. Now, one more view here. This is a view of a big city here and what you see here is a castle here and a better view of the castle. Today's picture, this is how the castle looks like and this castle is Tübingen Castle. Why this has become very important or at least why am I presenting it today? Let us look at the details here. I am showing a picture here. It's a simple room what we see here and this is a kitchen in the a kitchen in the castle. Now, this is the place where DNA was actually discovered, the room where DNA was discovered, which has seen a tremendous growth in medical history today. We know the importance of DNA, and I'm highlighting a portion here. This is the place where actually distilled water was extracted, apparatus for extracting distilled water, and I'm highlighting one more stuff here. This picture was taken in the year 1879. Almost around this time only DNA was also discovered, and he had called this substance as nuclein. The word nucleus or nuclein was used by Sir. Now let us look at the last personality for the day. This person is Felix Hofstadter, and he has done tremendous contributions to hemoglobin, regarding hemoglobin. And this person introduced the term protein, what we are calling today as protein here. And he founded the journal which stands today as Biological Chemistry in the year 1877. And if any students are listening to us, it should be a dream for us to publish at least one paper in the journal Biological Chemistry. I have not done, and hope in future I could make it possible, because this is a very good journal which stands from the year 1877 onwards. The last image for today's presentation, this is the Castle Laundry, where actually DNA was discovered, where these two great persons were working together, and they had discovered the word protein here, or protein as they were calling. Now, I wanted to speak about all these persons for one specific reason. Like first we had checked with Boole. Boole, we knew that he had no academic background at all. And the other person had discovered DNA, and protein was discovered, and it was labeled in a very small, simple laundry like this. They were not looking for any sophisticated laboratories. And this COVID period, we teachers have a lot of complaints like I do not have internet facility, I do not have online and other stuffs. And students, you will not give up at this period of time complaining about what is not available. A passion for doing things and a determination to do things will actually lead to outstanding discoveries, as we have seen what these people, great people, have been doing. And I wish that some of the students, if you are listening to me, research scholars, don't give up for anything which happens. If you are really working hard with passion for doing things, definitely you will be remembered in tomorrow's world as we are remembering Boole as Boolean algebra today. With this word, I would like to go for the last part of the presentation, that is mutation identification using Hamming distance. So we have Hamming distance over here. That means that we had the Haze diagram. From the Haze diagram, we understood that hydrophobic to hydrophilic property could be represented, and they had understood that they can study about gene mutation using the representation of a Haze diagram. Next, they are defining a Hamming distance to be the distance between amino acids, with one more word over here, the mean distance between the respective codons. So I take the same amino acid table only. Let us see how this could be done. We are going to pick the codons from this table. I shall explain with an example. Now take this amino acid table. Let me pick glycine here. I am highlighting it here, and I am picking cysteine. So now we have picked glycine and we have picked cysteine also. Now this is the binary conversion table we initially had checked out, where G, A, U and C are replaced by 0, 0, 0, 1, 1, 0 and 1, 1 respectively. Let us do the same for glycine and cysteine here. Now what we try to do is, we have to pick this first codon here, G, G, U here, and we have to go for finding the Hamming distance with UGU and UGC first initially. Take a codon here and do it for every combination of cysteine. Let us see how this could be done. I'm taking the binary conversion here, so you can understand G is representing, as you see here, it is 0, 0. So I've taken a 0, 0 here, 0, 0 here, and 1, 0 here. Now let us find the Hamming distance. It is equal to 1 for us here. Like we already have seen how we are checking out for the Hamming distance. So the value is 1 here, and again I try to find the second combo here. The value is equal to 2 in this case. Now this way we have to find all possible Hamming distance. Take the second combo GGC, find out the Hamming distance with UGU, UGC, and continue this procedure. Now what happens is, the distance is calculated to be equal to 16. The authors have defined it to be as the average value. Totally, we have calculated the value to be equal to 16. So the estimated value is 16 divided by 8. 8 combinations are possible. The value equal to 2 for us. Let us look at one more combo here. The same amino acid table. I'm taking the same glycine, but now I'm picking arginine. See, we need to be a little bit careful. I'm highlighting it here, arginine, but we have one more combo here. So I need to pick this combo also. Now let us forget about the table. Now we are trying to compare glycine with arginine. Both the combination of arginine needs to be taken. Once again, go for the binary conversion here. Go for the binary conversion of arginine. So totally 4 combinations here and another 2 combination of arginine. All 6 combinations need to be taken into consideration. Now, there are 24 total distances to be calculated. Like you calculate as GGU with all the 6, then GGC with all the 6. Similarly, GGA with all the 6 and GGG with all the 6. 6 4s are 24 distances should be calculated. And the distance value is calculated as 64. That means that Hamming distance will be 64 divided by 24 for us. That's what it's calculated here as 2.66667 for us. Now, 20 amino acids are there. See, when we say 20 amino acids, we need to remember one thing. In general, in the literature, there are more than 300 amino acids. What the authors pick here, or what we in general consider as 20 important amino acids, are the amino acids that play a crucial role in the body metabolism. The other amino acids are still existing, but they are not considered that important in day-to-day study because of this reason. Now we have calculated the Hamming distance. I told 20 amino acids. That means that we have to calculate 400 values like this. And the authors have done that. I'm presenting the table for you here. It's a huge table. It's a 20 by 20 table. 400 entries are available here. And I'm highlighting what we have calculated as 2 and 2.67 respectively. Now this is done. Let us see what the authors tell about what this table is conveying. The maximum distance corresponds to the transversion in the second basis of the codon. When we tell second basis of the codon, now we understand hydrophobic and hydrophilic. U in the second position means it is hydrophobic, and A in the second position means it is hydrophilic for us. Next. They frequently alter the hydrophobic and biological functions. See, they say larger value means, that means that a transversion occurs. That means that hydrophobic becomes hydrophilic, which definitely means that something which was not water absorbent now becomes water absorbent for us. That means that the biological property of the protein is getting affected for us. And then between codons of hydrophilic and hydrophobic amino acid, there is a larger Hamming distance. So somewhere you see here, you see data like this. I'm highlighting it here, 4.5, 3.83 and all. So this probably is going to be a larger 4.67 we see here. Larger Hamming distance means, it means that it is between codons of hydrophobic and hydrophilic. When we try to compare them, value becomes larger. And finally, in general, amino acids with large difference in their properties have larger values. So not only this table is being constructed, it is also related with the biological properties of the amino acids. Now, I want to show a table here. Only 2 more tables. The first table here. Let us read what this table is about. It is about the Hamming distance of the mutations found in the HIV gene that converts to the drug resistance with regard to the wild type of HXB2. See, I don't understand much about what is HXB2. As a maths person, what I understand is mutations have occurred. The first column represents amino acid mutations for us, and there is a change in the codons for us. That is, there is a change in the protein, and the drugs that are referred to is also listed out in the fourth column here. Now, the third column is what we are going to concentrate on. This is representing what we call it to be as the Hamming distance for us. So, first column was amino acids for us. That is mutations occurring, the labels given to them, the codons where it is occurring, the changeover in the codons. CUC has become UAC, and the drugs that have been antiviral drugs that have been prescribed for this particular changeover. Now this DH value is important to us. When we keenly look at these two data, we see that most of the data is 1 and 2. So when mutation is occurring, most of the data is turning out to be 1 and 2 for us. Let us check another table. This is the last table for the day. Like once again, amino acid mutation, it is listed out here in the first column. It is in the name of a label. Maybe a biologist might understand this better. And this is related to the mutation found in human beta globin gene. And this is a changeover in the codons. And this is the biological effect of the codons and probably the references that the authors had used here. They have used so many references, and now what is important for us is this DH value, that is the Hamming distance value for us, and most of the cases we observe here it is 1 and 2. It's 1 and 2 in all the cases here. Now this is what the author also concludes. The conclusion is small differences in the biological activity between the wild type and the mutant gene would mean a smaller Hamming distance. So whenever there is a mutation, the Hamming distance value is small, and this they call in their terms to be as continuity hypothesis. Now we come to the conclusion part. Concluding, we have seen that if you are constructing the Hamming distance table, and if you see a value to be as 1 or 2, the Hamming distance value between two proteins to be as 1 or 2, then probably there is a possibility or a gene mutation has occurred. A minimal Hamming distance means that a mutation is there. Now, I have come to the conclusion of my presentation. See, we had started out with Boolean algebra, and then slowly we had drifted off to amino acids, and then to constructing the Haze diagram, and finally using Hamming distance we are trying to predict something about what we call as gene mutation. This has been presented today with one understanding that if at all somebody is listening to me and if things are new to you, we can actually try using some of the algebra properties that we are strong enough with. We have learned a lot of algebra in a UG and in a PG also, and later if we have taken a PhD with algebra, our algebra base is very strong, and now we understand that we can combine this mathematical part in a very different dimension. And maybe this thing which we have understood today, that is drawing a lattice and trying to relate it with mutation, we can try studying new biological properties, and I'm hoping that we would be able to apply our mathematical knowledge in a different dimension to predict something or to lead to some better results rather than the existing ones. And these are some of the references. The entire presentation I have done is reference number 1, the genetic code Boolean lattice, which appeared in the Communications and Mathematical and Computer Chemistry, which appeared in the year 2004 for us. And these are some of the references. The mathematical part, of course, the regular standard book I had referred to, Temple and Manohar only. And with this, I would like to thank once again the management of Hindustan College for giving me this opportunity, the head of the Department of the Mathematics and the coordinators, Kausalya ma'am, for giving me this opportunity. And last, I would also like to thank the student coordinator Varsha for making this day very comfortable. My special thanks to her because students are putting an effort in this period, and I hope that at least Varsha was at least one of the students who was listening to me, and in future I'm expecting students to do better things in relating mathematics to other subjects also. And I once again thank all the audience for the patient listening throughout the session. Now I stop the session here, and if any questions from the audience, I'm getting back to the audience for questions if any.
Ma'am?
Yes, ma'am.
Ma'am, question already you gave the answer, references and books, ma'am. And another question is, which book is preferable to learn Boolean algebra for beginners?
Ma'am, beginners, Tremblay Manohar is the right book, ma'am, because it will never misguide anybody, ma'am. There are no errors in the book, and it will explain things right from the scratch, and it is one of the best books that I have read, ma'am. So Tremblay and Manohar, they can start off with for anything related to discrete maths, in my opinion, madam.
Okay, ma'am. Thank you, ma'am. Your talk was really excellent, ma'am.
Thank you,
gave information about application of Boolean algebra, ma'am. Thank you, ma'am.
Thank you, ma'am.
I call Kritika, ma'am, to present the vote of thanks.
A very good morning to one and all with a heart full of gratitude to God. On behalf of our management and Department of Science and Humanities, I take this opportunity to propose vote of thanks. I extend my sincere thanks to our resource person, Dr. M. Yamuna, for her enlightened speech and inspiring presentation. Thank you, ma'am.
Thank you, ma'am.
I would like to thank our head of the department, Dr. K.P. Uma, for her motivation and enthusiastic support. Thank you, ma'am. My gratitude goes to my faculty coordinators, Mrs. B. and Dr. R. Purnima, for their valuable input. Thank you, friend. My special thanks to the student coordinator, Ms. Sri Varsha, for her technical support. Thank you, Varsha.
Thank you, ma'am.
My sincere thanks to the participants for their active participation and involvement. Thank you, participants. Once again, I thank one and all.
Thank you, ma'am.
Shall we wind up?
Yes, ma'am.
Thank you, ma'am.
Yes, ma'am.
Thank you, Amino.